who appropriately is going to tell us all about multi-party communication compatibility, which is definitely an appropriate topic. What it has to do with gossip.
Great. So it's my first experience to have a talk as an intermission into an invited talk. This is a bit of a weird experience. Okay, so do you have 10 minutes or
yes.
what, until the speaker comes back? Okay, so I'm going to tell you about some joint work with Marco Carbone and Carsten Sherman about forwarders as process compatibility. So Ornella's talk this morning was a good introduction to mine, because mine starts also with binary session types. So as she said, we have a version of the pi calculus to represent processes. And in our work, we used what she presented, the connection with linear logic, to type those processes. So we used the tensor products as a symbol for output, and the inverted ampersand, the par connective as input, and we read everything sequentially because it corresponds to the pi calculus, so we always bracket everything to the right. So I will remove the brackets, but that's how you have to read the types. Right. So, and then the proofs of linear logic correspond to the processes, to the typing of the processes. And so that's what Ornella presented this morning. So propositions are types, proofs are processes, and what I care about in this work is the way reductions correspond to communication. So basically, these two processes, one sends an A and receives a B, and the other one receives an A and sends a B. And it seems like they are ready to communicate. So the communication, as Ornella already mentioned, in the original correspondence between linear logic and session types, was represented as the cut rule, where the two types of the processes that are communicating need to be dual. So here they can communicate because one sends an A, the other receives an A, and then the second one sends a B and the first one receives a B. And that's duality. So the point of this work, one way to see the point of this work, is as a generalization of this idea to something that is more general, more expressive. So this cut, the traditional cut in linear logic based on duality, restricts our semantics to synchronous behavior and our sessions to binary sessions, two participants in each session. So the first generalization is to generalize to multi-party, which means more than two participants. So for example, here it's the first participant only sends an A, which is received by the second participant, but then the B is not sent back to the first participant, but to a third person. And this has already been studied by Marco and others, Sam as well. And one way to generalize this is to use a concept called coherence. So we want these two processes to be seen as, three processes are represented as three linear logic proofs with their three linear logic types, and we want to introduce some sort of cuts that generalize the normal cut to cutting three things instead of two. And to this, you can't use duality, so you have another notion which is called coherence, and so basically the three types, A1, A2, A3, have to be coherent for this cut to represent communication. And the coherence is doing really a generalization of duality in the sense that, well, it does what you think, like it matches the A from the not A in the type, and then it matches the B with the not B, and it closes everything. So I'm reading the proofs bottom up, the derivations bottom up. Okay, and so that was the way to generalize to multi-party. And we also want to generalize to more processes even in the binary case. For example, when the sending operation of the A and the receive operation of the A appears at a distance. So it's this situation where the two processes send in parallel and they receive in parallel. And this is not a deadlock, that they can do this if they behave asynchronously. And so here again, we want to write this kind of a cut, and so we want to use another generalization of duality between the types A1 and A2 that makes it possible to make these two processes communicate. And so the way to do this is to use some sort of buffers. So basically, they send the message into a buffer that buffers both A and B, and then it can be sent also in parallel. So we add now this sort of structural extra structure in our judgment that plays the role of the buffer. Okay, so and that kind of we call this a crisscross. I mean, I'm sure many people call this a crisscross because it like does this thing of crossing in parallel. But I think it's a good metaphor. And so then the question is, can you generalize in those dimensions? So do it in the multi-party case, but still by keeping this asynchronous semantics. So you want to be able for process 1 and 2 to send their message A and B in parallel, and the messages to be received after the other parallel send. And so that's the point of this word, and that's this work, and that's the point of forwarders. So again, we have these three processes, and we want to generalize our notion of coherence, of coherence to something asynchronous, and we introduce the notion of forwarders. And so these three things can communicate if there exists a forwarder. Actually, there is a typo. If there exists a forwarder between the dual of the types. This one is going to be correct. So it also uses buffers, but because we have more than two parties, we have to remember who the buffer belong to. Who the buffer, who is going to receive the message that's in the buffer. So now we annotate the connectives with the recipients of the message. So the first power connective gets a label x2 because the message A is going to go to process 2, and the second power connective gets the label x3 because the message goes to x3. And same for the buffers. Buffers are annotated. But otherwise it's the same, and then again you can you also have to annotate the tensor, the output, to be able to match it with the right buffer. Otherwise, it might create problems. And so, yeah, I removed the typo from one side to the other. That's the forwarder has to be between the dual types. And the reason for that is that you have to picture that the process sends something into the buffer, and the buffer inputs it. So that's why it has to be dual from the point of view of the buffer or the forwarder, the person in the middle. So that's the idea, and so we call this asynchronous forwarders. And the cool thing about it, and the main result, is that asynchronous forwarders actually characterize precisely a notion that is already present in the session type community, which is multi-party compatibility. So it's more of a semantic notion. It's been around for a while, but it's been refined by many authors. And our result is exactly that. There several types are multi-party compatible if there exist forwarders that allow you to derive that type. And also forwarders are, what's the word? They can be combined together by an internal reduction, and so if you combine two forwarders together, they are still forwarders. And the details are in this archive paper. And that's it. Thank you.
Thank you for a wonderful talk and graphics. We have time for maybe one question, because I've been told that the keynote speaker has actually gone back online, so we can have
that's
the other
much more important.
Session questions. So I guess I'll go do the running.
Thank you. So now that you name basically where some message has to go, right? So it's specifically assigned to a particular recipient. Does that not allow you to reduce this again to binary session types by having basically one connection to everyone? Not sure.
I'm not sure what you mean, because if we were able to reduce it to...
Well, I guess not, but I'm trying to understand why.
I think it's still multi-party, because you still have this thing that one communicates to two and two communicates to three. Yes. But you can, maybe what you mean is that you can project somehow.
Okay.
Yeah, I'm not completely
let's
sure.
Talk about that later.
Yes. Okay. So, are we ready to reconnect, or can I have one? Yes.